Okay, this is the introduction for Lab 4. This lab is being done in Google Earth. So if you don't have the Google Earth software already installed on your computer, you want to download that. Just do a search for Google Earth, find the software and install it. It is free and it is an exceptional program. It's sort of like Google Maps, but a lot more in-depth and a lot more inclusive. Shows places where there are no roads, shows the whole Earth. You'll want to download the Google Earth Lab document here, Lab 4 document. And it'll look like this, and you'll have a list of coordinates to go through after you've read through the instructions. However, when you go into Google Earth, whether it's the first time or if you use it on a regular basis, you want to make sure that the settings are set appropriately for doing this lab. To do that, to adjust the settings and or check your settings, you want to click on Tools and click Options. A couple of things you want to do is make sure it's in decimal degrees. Make sure the vertical exaggeration is set to 1. Later, in the lab, you can adjust that up. I recommend adjusting it to 3, but to start with, you want to make sure it's set to 1. Make sure it's set to meters and kilometers. The default is different.
Let me think.
Sorry, my phone thought I was talking to it and started responding there. Anyway, so make sure it's set to meters and kilometers, set to decimal degrees. High quality terrain, you want that check marked to enable it. So you want it to be using the high-res images, and you also want to use 3D imagery. This is going to allow you to see hills as hills when you zoom in and start tilting the camera, instead of having it look just like a flat image. So you want to have those turned on while you do this lab, and then hit Apply and hit OK. Then I'll walk you through the first fault here. It's actually the one shown in the picture in the lab. You can highlight both coordinates at the same time. Do either right-click copy, or you can do Control copy on your keyboard, or if you're using a Mac, I assume Control C is copy for the IBM. I think Command C is copy for a Macintosh. If you're a Mac user, you'll know if I'm wrong and you can laugh at me, but hopefully you know how to do a copy and paste. This box right here, you do your paste, Command V, or right click on the mouse and do paste, hit enter, and it'll start flying you into the location. But it's going to zoom in to whatever elevation it thinks is appropriate to see that location. But in the lab, this third column is called altitude. This is how high you want the camera to see the fault that I want you to look at. Where you see that is this thing called eye altitude down in the bottom right corner where my mouse is circling. And you can see that currently it's showing an eye altitude of 2.31 kilometers. We want an altitude of 10 kilometers. So we scroll the mouse wheel until it's right near 10 kilometers. And now you try to see the fault. In this case, we can see there's some structures that seem to be offset. this gray line suddenly jumps way up here, and we see a stripe along here of like stretched material, and we can see other, just the repeating pattern. If we scroll out even further, we can see that other things like this kind of green and this orange are repeated here. And so hopefully your immediate thought is, oh, this is a transform fault or a strike slip fault, where this right here, I'll use a path tool. That little white line that I drew indicating roughly the motion of the fault. Hopefully you could see that quickly. This is a little bit easier fault to identify, but even once you say, okay, it's a strike slip fault or a transform fault, you need to say, is it a right lateral or left lateral? Did it move to the left? Did it move to the right? Also a sinistral or dextral are the other terms you learned in class. The way to tell is if you stand on one side of it, say you're standing right along the gray stripe here, and you're on the west side, and you look across the fault. Is the rest of the gray stripe to your left or to your right? And this time, if you're standing right here and you look across the fault, clearly it's to the left. The cool thing is it doesn't matter which side of the fault you pick to look at. If you're standing on this gray and you look across the fault, the rest of it is to your left. So this is a left lateral strike slip fault. Now, a couple of things that you can do, because some of the faults are a lot harder to identify from the aerial view. You need to be able to zoom in once you've figured out what you're looking at and look for ways to identify, is this a normal fault or a reverse fault? So one thing you can do is just scroll with a mouse wheel. If you hold the shift button, you click and you drag, you can tilt it. When you tilt it, you can see, the hills look like hills, the valleys look like valleys, but it may not be very distinctive. So you can go into Tools, Options, and change that vertical exaggeration to 3. That's the maximum that Google Earth can handle. Hit Apply, and OK. And now you can see the hill is much steeper. The only thing to be careful of is the camera's not in the same relative location anymore, because the ground has basically grown taller. The camera's not in the right place. So we tilt it back, we zoom out, we find our yellow pin. Now we can zoom in and we can tilt it, and we can see things that we couldn't see before. For identifying this particular fault, this is much less useful, but the technique that I'm demonstrating right here is very useful in many cases. So if we look over here, we can see this ridge, we can see this low area, we can see erosion on the ridge, we can see less erosion down in this flat area. Things that'll be useful in the next lab are noticing the banding on the ridges that we can see. So, moving it around, changing the tilt, zooming in, zooming out. These are very useful techniques for identifying the fault that you're supposed to identify. So this one, we've got the left lateral strike slip. You would fill that in. You can type in the document, or you can print it out and write in it and then scan it. Either one is fine. Let's look at another one here. Put it in. Let it zoom to it. And now we say, okay, altitude of 2. It's too high this time. So we'll zoom in a little bit closer to make sure we're looking at the thing in question. And we see, this line here is the fault. If we zoom out further, now that we've verified, yeah, that dark line is the fault, we can kind of see more of what's going on. Zoom back in. We can turn it and tilt it. Say, okay, we've got this dark line. There is vertical exaggeration going on. If we want to remove it to see what it looks like normally, we can do that real quick. Now, of course, we have to find our yellow pin again. There it is. Notice the land is a lot flatter now. It's not stretched vertically. But we've still got our dark line indicating the edge of our fault. We have a slope on one side and much lesser slope on the other side. There's no offset of the black line, so unlike the first example, this is not a strike slip fault. The two options that remain, of course, are a reverse fault or a normal fault. It requires identifying which is the hanging wall, which is the foot wall, and whether that hanging wall moved up or down relative to that foot wall. This is where turning the camera, tilting it, looking for the erosion especially, is very useful. You notice in these hills there's deep erosion. Out in this lower part, we don't see much of that erosion. If anything, maybe a little bit of that is being deposited here. So this tells us that this block here is not moving up. If the right side, the way I have the camera oriented, were moving up, there would be erosion in it. If it has moved down, it is now lower, it won't get erosion, it exposed things, made this left side into the high ground, so the water started eroding it. So if this side dropped down, leaving this side up high, we get erosion on the new high ground. Erosion always happens on higher ground, eroding towards lower ground. So that tells us this is a block that stayed in place. If you look at the slope involved here, right along the edge of the fault, it's all sloping. I'll turn the camera back here. Sloping down to the right. So it's not logical that this left side was thrust up. It's much more logical, looking at it, that this right side slid down, and that's actually the fault scarp face, where the rock was scraping down, and this is where it stopped. That makes this left side, which if you look at your little compass up here, is actually north. If we click that N, it'll orient it back, so north is up, and we see the uphill side to the north. I hold shift and turn it and tilt it again. So the north side is a foot wall, The south side is the hanging wall that slid down, making it a normal fault. And so in the block here, you would need to identify this is a normal fault, hanging wall to the south, footwall to the north. And that's how you would identify that fault there. And so then you go down the list and you do this for each of the faults, identifying is it a normal fault, is it a reverse fault, is it a strike-slip fault, and then something about the orientation, where's the footwall or the hanging wall, if it's a normal or a reverse. If it's a strike-slip fault, you have to identify is it left lateral or right lateral. Then that's part 1. And then for part 2, you just want to or need to talk a little bit about it. This is sort of like a conclusion in a lab report. What is the hardest part for you? And do you think that you'll be able to do this based on looking at them in Google Earth and being able to pan around and see the landscape? If you were out here actually standing, if you drove out on this road and then out into the hillside here and looked at this standing there personally, would you be able to say, okay, I can see the line of the fault and I can see the slope and I can see the erosion. I can tell this is a normal fault. Because that's the goal, is to be able to take what you're seeing in Google Earth and think, you know what? If I were looking at this in real life, I'd be able to identify the exact same features and structures and tell you what was going on. Just email if you have any questions, and we'll get back to you as soon as possible.